So here all we're really going to do is look at some examples for classifying molecules. So we've got our general flow chart already set up here. We'll give it a second to clear the directions or the navigations down below. And you should remember these. I would, because our exams are officially going to be open note, I would definitely print this out and have this handy when moving through really all of our exams. Okay. You still need to practice it, so that's what we've got here. So within this, we've got 4 structures, which means we're going to have 6 potential relationships that we could go through and identify. We could look at A to B. We could look at A to C, A to D, B to C, B to D, and C to D. Okay, so we've got all 6 of those relationships that we need to be able to nail down. With that said, let's go ahead and pop up a quiz question. And now we want to kind of walk through and see what's going on within these relationships. So if we start, I would recommend that you want to try and find where you have key differences. Okay, so for instance, we notice right there that that alcohol position is changing potentially. So I'm going to label that as a key kind of signifier. The next thing that I'm going to go through and note is that I do see that position potentially changing as wedges and dashes. And I'm going to switch to a different color for D because that one is way out of whack. So what's going on with that? We've got this extra methyl group. Does that make it different? Okay, it has a different methyl, so maybe it is different. But we have to realize that all we went through and did was we took a CH3 from being connected here, and we've now moved it to being there. So we haven't actually changed the formula. The formula is the same. This is not technically a different structure because we have the same formula. Okay? What it is going to mean is that it is a structural isomer with everything else. Okay, so we'll call that in as structural because we've changed that location. So that's a nice one to nail down because that switches it up pretty quickly. The next part, as far as identifying, we could really just pick any spot we wanted. So I'm going to compare A to B, and we go through and compare this. We'll note that the red position we did switch. Right? And if we were going to look at kind of a mirror image on a structure that was chiral, whoops. If we kind of flipped that so that we got the alignment correct, we would notice that in that mirror image, we're going from wedge to dash. So as long as the backbone stays constant, a switch of wedge to dash is a mirror image. So we are doing a mirror image at that red position. But for A and B to be full-on mirror images of each other, every chiral atom has to make this switch. So let's go ahead and take a look at that blue spot because we identified that as being important. Is that also a chiral atom? Well, we have carbon, 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 and hydrogen. Well, that really says we have just two things that are the same because all the carbons are the same. Well, the bottom carbon is connected to an OH, and the top 2 are connected out to carbons. So that bottom carbon is unique from the top 2. Are the top 2 different from each other? Well, one is connected to a double bond further on down the food chain. The other one is not, which would suggest that those top 2 carbons were different. We do indeed have a chiral atom there. Okay? So now we have to decide, when we're looking at our red relationship, did we also mirror image at the blue position? Well, no, we didn't actually mirror image there. That stayed constant. So since we've only mirrored part of it, we're not looking at enantiomers. Okay? They aren't superimposable, so we don't have to worry about meso. This really means we're looking at our diastereomer. Stereomer for our relationship. If we go through and make the comparison between A and C, what do we note change? Okay, well, at the red position, we went from dashed to wedged. Right? At the blue position, we went from wedged to dashed. So they both mirrored. If they're both mirroring, we're looking at enantiomers. Okay? And we'll show that superimposability here in a second. Last but not least, B to C is going to come in as a diastereomer. Again, we're only mirroring one part. We mirrored the blue atom, we didn't mirror the top. Okay, so those would also be diastereomers. To get the enantiomer one, let's go ahead and start with C and draw a formal mirror image. As we draw out our mirror image, we would end with this structure. You might say, well, that doesn't superimpose. So what I'm going to do is flip the structure on this axis. I just kind of rotate it around. As I rotate that around, the double bond is now going to be on the other side. What was wedged, because it was coming at you, and this is where I would gesture, unfortunately I can't gesture, if you aim your thumb at you and you flip the structure, that thumb is now going to be aimed away. So that gets us our dashed. There's our OH. Okay. What happened with the dashed? Well, if your thumb was aimed away from you, it would become wedged when we flipped. Okay. What's the relationship between these two? Well, those are indeed superimposable. Okay. So I know A and this are superimposable. I know this and this are the same. And I know this and this are mirror images. So what does that mean? I know C and A are mirror images that are not superimposable to start. Okay? And that's kind of the manipulation that I would go through. That's a lot of structure drawing. And I would argue that structure drawing is easier to do than building the models because the models are fairly large in this case. But it's those kind of manipulations and recognizing where things spin, flip, and rotate that's going to allow you to draw and quickly identify these relationships as efficiently as possible. Okay. What if you have multiple stereocenters? Okay, so, and we saw it kind of with the previous one, there were multiple stereocenters. We can encounter kind of a different question, and that question can be how many possible stereoisomers are there? Okay, and there's this rule 2n and minus 1 per mirror plane. And really what we're trying to get at is what are the possible ways that we could combine wedges and dashes on this particular structure. For me personally, when it's simple, what I would go through and do is say, okay, well, it could be wedged chlorine. If it is a wedged chlorine, then that other chlorine could be wedged, or it could be dashed, right? So those are two possibilities. But that first chlorine that I started with could have been dashed. Okay, and by that same token, wedged or dashed. This way I've covered all of the possibilities. If we have 3, we do a similar process, and yes, it becomes tedious to deal with. Now when we go through and look at these, we have to decide, are each of these unique stereoisomers? Okay? You might say that the diagonals look awfully similar. Okay? And it turns out that yes, those diagonals are pretty similar. These two end up being identical. There's an internal mirror plane. The relationship between those two is that they are meso, which means I should cross one of them off. It's not a possible stereoisomer because it's a repeat of the one that I've already drawn. Okay? When we look at the other diagonal, it looks suspiciously like we could superimpose it. Okay? If you go through enough manipulations of rotations and flips and spins, this is one I'd recommend actually building a model for, you'll find that they are actually non-superimposable. And they are indeed mirror images. It takes a little bit to align that, but those are actually enantiomers of each other. And then lastly, we would have our diastereomers. Okay, very quickly solved. How does this go through and apply with our total stereoisomers? Well, 2 to the n minus an internal mirror plane. So when we looked at our starting structure, the first thing we would have to do is identify that these two positions were chiral atoms. How do we know that? We go back and we count out hydrogens, or not hydrogens, how many distinct groups? 1, 2, okay, carbon versus carbon, is there a difference? No, so move out 1. Carbon versus chlorine, there is a difference, which means our starting two carbons are unique from each other, and we'd have to label them in. So that position has 4 different things. That would be a chiral atom. Okay, we do the same thing with the other position. Okay, again, slowly reaching out to each of the positions around it and deciding, is there a difference? If we can't find a difference, we move 1 atom further away and 1 atom further away until we find a difference, or we tie back on itself. Okay, which we'll actually see in an example in a little bit. Okay, so we won't stress about that. Okay, so when we go through and do that, that structure then comes in with 2 stereocenters. If we go through and use our formula, it's 2 to the n, where n was the number of stereocenters, is 2, which means I get 4 possible stereoisomers. But I do have that mirror plane through the molecule, -1, 3. Where's my 3? They're the 3 stereoisomers that I drew up. Okay, that went awfully fast. You will see more advanced questions with that. Typically, when we're looking for those mirror planes, you're looking at very few stereocenters, 2, 3, maybe 4, but even 4 is a bit of a stretch. So if you're seeing more than 4 or 5 stereocenters, there probably isn't an internal mirror plane, and it's just 2 to the number. Okay. Before we start getting weird things, that doesn't mean 2 times that number. 2 to the power of, like 2 to the 5th is a little bit different than 2 times 5, right? Okay. With that, my computer's mildly freaking out. Let's see, can I advance? Well, I can advance. If we take a look at this structure, chloramphenicol, how many possible stereoisomers would there be for this particular compound? So again, to answer that question, we have to go through and look at each of the carbons and decide, does it have 4 distinct things? Okay, 4 distinct things means sp3 hybridized. So if we see double bonds, it ain't sp3 hybridized, we can ignore that. So the entire benzene ring, ignored. Okay, my technology isn't working nicely with me, so we're just going to have to talk through this. The extreme right carbon with the 2 chlorines. 2 chlorines. 2 chlorines are the same, which means that can't possibly be a stereocenter either, because I can't tell a difference between those. Okay, so now we're left at looking at 1, 2, 3, 4. We'll go ahead and look at the nitrogen too. Okay, there's 4 things. Okay, with the carbonyl now purple, that's sp2. Get rid of it because sp2, we need the sp3. That blue position, if we draw in our hydrogens, well dang, we get 2 hydrogens to satisfy that octet, also identical, not a stereocenter. If we go through and look at the rest, hydrogen, hydrogen, and for the nitrogen, we have a lone pair. So with the purple position, do we have 4 distinct things? Well, oxygen, hydrogen, carbon, and then an sp2 carbon. So yes, 4 different things, that's a stereocenter. The orange one, we would go out to hydrogen, nitrogen, carbon, carbon. Okay, these are both carbons, but can I tell a difference between them? Okay, one is a CH2 and the other one is a CH. So yes, there's a difference between them. Because there's a difference, the orange one is also a chiral atom. And now we're going to move to potentially the trickiest of this. The nitrogen, lone pair, hydrogen, carbonyl, and then carbon. Do we have 4 distinct groups around that nitrogen? Well, hydrogen, carbon, carbonyl, carbon, lone pair. The lone pair becomes a little bit weird. That is a distinct group, and in this configuration, that is technically a chiral atom. However, one of the issues with that lone pair is that it can oscillate up and down through the nitrogen because those electrons belong to the nitrogen, not on one side of the nitrogen, but anywhere on the nitrogen. And so what can end up happening if we looked at it from the side is that that lone pair can be up above and it can migrate itself to be down below. That ultimately causes a mirror image shift between it, and it's because of that oscillation back and forth that the nitrogen with a lone pair, or really any atom with a lone pair, won't be a chiral atom because how the electrons are tied to the atom. Okay? It ends up rapidly interconverting in between the possible stereoisomers. Okay? What does that mean for us? The nitrogen is not a stereocenter. So there are 2 stereocenters in this molecule. That means there are 4 possible stereoisomers. This is a drug. I wish I remembered which drug it was. If we have any potential pharmacists in the class, feel free to post into our discussion board what chloramphenicol is as a drug. With these 2 stereocenters, one of those stereocenter structures is likely to be the active drug. The other 3 aren't. If one of those other 3 is toxic, we now have a problem, right? Which means if we're going to go through a synthesis to make this molecule, we have to ensure that we get the one that is active and we ignore the other 3. That makes synthesis of a drug with these chiral atoms very challenging because some of our syntheses lead towards multiple products, okay, as far as stereocenters go. So we do have to be aware of that when we're moving forward through the rest of our chem, okay, or our syntheses. So we've got our last example. I believe this is, the last slide. So what we want to do is identify if the molecule can be chiral by marking all stereocenters and then determine the possible stereoisomers. So again, 3 examples. We'll give you a second to try and work through some of these. And we're going to quiz you on it. Okay, so let's start with that first one. If we start with that position where we see the wedge in the dash, we can go through and identify 1, 2, this is a CH2, this is a CH. Those are distinctly different. We get 4 different things. So that blue carbon is indeed a stereocenter, which means I have 1 stereocenter. Okay. Before I get too antsy or excited and be like, oh, that's it, I can just move on, we should verify that none of the other sites are stereocenters. Okay. And what we should see is that's true. There aren't any other stereocenters because this has 2 hydrogens, 2 hydrogens, 2 hydrogens. Up here with the double bond, we have the potential for geometric isomers, but it's not going to generate a stereocenter because of the symmetry of that structure. Okay. So 1 stereocenter. If we were to look at stereoisomers for this, we'd be looking at 2 to the 1, which is 2 possible stereocenters. We either have that methyl wedged or we have that methyl dashed. Move to the next one, be like, well, man, we've been doing this too much. There's our wedge. We have 1 stereocenter, and so there we are, and we move on. But we'd be wrong. Why would we be wrong? So again, this is why it's important to go through and look at each of those pieces. Our hydrogen dashed, yes, chlorine versus hydrogen. Carbon versus carbon, can you tell a difference? Well, no. So what do? We move 1 carbon further, or 1 atom further away. We move to carbon versus carbon. Again, can't tell a difference. I move 1 atom further away. Note the crossover of my arrows. I can't tell a difference. I can't tell a difference through the end of the structure, which then rubber bands back to tell me that these 2 positions are not different, okay, or not distinguishable, but distinguishable is too hard to spell, okay, which means I really only have 3 distinct things connected to that carbon, which means there are 0 stereocenters, none. Why show the wedge? Maybe we were trying to show the wedge to show where the chlorine was in this particular drawing. More than likely, In this case, the wedge was shown to trick people into saying that that was a stereocenter to incorrectly answer the question. Okay, so please be careful. Don't just say we see wedges and dashes, that means stereocenter. It doesn't necessarily mean that. Last one, we go, oh, well, no wedges and dashes, so it can't be any stereocenters. Again, we have to be careful with that labeling, and we should be going through to identify. If we take a look at that top position, note what I'm keying in on or where I see three things bound. Those three things usually help out because I'll have a fourth as a hydrogen. Okay, we've got CH3, CH2, CH2. I can't tell the difference between the carbons. Move one further away. I get a CH2 versus a CH. Those are distinctly different, which rubber bands me back. And I can tell the difference between those two positions, which means that is a potential stereocenter. As I continue around, again, I'm going to look for a carbon that has three obvious things attached to it. There's my fourth with a hydrogen. Oxygen, hydrogen, I can tell a difference. CH2 versus CH. I can tell a difference there, which means that red carbon that I started it at is also a chiral center. Another position of three things. We'll count that one out. You will also find that that is also a chiral center. And then we have, lastly, that black spot, which is also a spot that has three different things, and you will find that that is not a chiral center. Did you hear that carefully? That one's not a chiral center, because when we go through and look at that, CH3, CH3, I can't tell a difference between those two, which means not a chiral center. This molecule has a whopping total of 3 stereocenters, which means if I were to look at the potential stereoisomers, this is 2 to the 3, 2 times 2 times 2, which gets me 8 possible stereoisomers. Okay? With that, we are almost done. I am going to force you to watch one more video, and that one more video is going to look at the nomenclature for these for chiral molecules. So that's R and S. How do we assign R and S? That will be the end of Unit 1. With that, thank you for listening. You've made it all the way through. Congratulations, a quarter of the way done. It only gets harder. It gets harder, I think. But it's more fun.